Every single day, organizations worldwide deploy software that has never been properly threat modeled. And that is precisely how the worst security breaches happen. In this video, you will master threat modeling, the single most important security activity that most teams skip entirely. We will compare the major methodologies, deep dive into Stride and LINDDUN, then walk through a real e-commerce system to find the exact gaps that attackers will exploit. Welcome to Evoluguard Academy. Let's begin. So what exactly is threat modeling? Threat modeling is the structured process of identifying, quantifying, and addressing security threats in a system before a single line of production code is written. It answers 4 fundamental questions. 1. What are we building? 2. What can go wrong? 3. What should we do about it? And 4. Did we do a good enough job? Here is why this matters in software development. According to NIST and industry studies, fixing a security flaw during the design phase costs approximately 60 times less than fixing that same flaw in production after a breach. 60 times less. This is why threat modeling belongs at the very start of your software development lifecycle, not as a compliance checkbox 3 weeks before release. Shift-left security starts with threat modeling. Let's compare the major threat modeling methodologies used in the industry today. Stride, developed by Microsoft, categorizes threats by type: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. LINDDUN focuses specifically on privacy threats: linkability, identifiability, non-repudiation, detectability, disclosure of information, unawareness of data processing, and non-compliance with regulations. PASTA is a risk-centric methodology with 7 stages that ties threats directly to business impact. Trike uses an asset-centric approach with risk matrices and data flow diagrams. VAST, or Visual, Agile, and Simple Threat Modeling, is designed to scale in Agile and DevOps environments. And DREAD provides a scoring system for severity, damage potential, reproducibility, exploitability, affected users, and discoverability. For software development, Stride and LINDDUN are the most practical because they are systematic, repeatable, and map directly to concrete security controls. In this video, we will focus on Stride for technical threats and touch on LINDDUN for privacy. Let's break down Stride in detail. S stands for spoofing. Can an attacker pretend to be someone else? This violates authentication. T stands for tampering. Can data, code, or configuration be modified maliciously? This violates integrity. R stands for repudiation. Can a user deny they performed an action? And can you prove otherwise? This violates non-repudiation. I stands for information disclosure. Is sensitive information exposed to unauthorized parties? This violates confidentiality. D stands for denial of service. Can the system be made unavailable to legitimate users? This violates availability. And E stands for elevation of privilege. Can a user gain unauthorized capabilities beyond their assigned role? This violates authorization. Every Stride category maps to a specific security property violation, which means every threat has a corresponding control or mitigation. LINDDUN is the privacy-focused counterpart to Stride. L. Linkability. Can different pieces of user data be connected to build a profile? I. Identifiability. Can individuals be uniquely identified from the data? N. Non-repudiation. Can users deny their actions, and should they be able to? D. Detectability. Can an adversary detect that certain data exists or is being processed? D. Disclosure of information. Is data revealed to unauthorized entities? U. Unawareness. Are users unaware that their data is being collected or processed? And N. Non-compliance. Does the data processing violate regulations like GDPR, CCPA, or HIPAA? In an era where privacy regulations carry multi-million-dollar fines, LINDDUN is not optional for any system that processes personal data. Use Stride for technical security. Use LINDDUN for privacy compliance. Let's apply this to a real system, an e-commerce web application. Our architecture consists of a React frontend running in the user's browser, a Node.js API gateway handling all client requests, a Python-based order processing microservice, a PostgreSQL database storing orders and customer data, a Redis cache for session and performance data, an external payment processor integration, and an administrative panel for internal staff. Users authenticate via JSON Web Tokens. The system processes credit card numbers, shipping addresses, and full purchase history. This is exactly the kind of architecture where a single missed threat model gap leads to front-page headlines and regulatory penalties. Let's threat model it properly. Threat modeling always starts with the data flow diagram. Let's build our step-by-step. Step 1, our external entity, the customer. Step 2, the web application frontend. This is our first process. Step 3, the API gateway. This is our first trust boundary. Anything outside this boundary is untrusted. Step 4, inside the trust boundary, the order service processes requests. Step 5, the PostgreSQL database, a data store. Step 6, the external payment gateway, another external entity. And Step 7, the admin panel, a separate process with elevated privileges. Now we trace every single data flow. The customer sends login credentials to the frontend. The frontend sends JWT-authenticated API requests to the gateway. The gateway forwards validated requests to the order service. The order service reads from and writes to the database. The order service sends encrypted payment data to the payment gateway, and the admin panel queries the database directly for reporting. Every arrow on this diagram is a potential attack surface. Every trust boundary crossing is a point where threats multiply. Now let's stride through every component and find the security gaps. Spoofing. Can someone forge a valid JWT token? If the signing secret is weak or leaked, yes. Gap identified. The JWT signing uses HS256 with a short 16-character secret. This is brute forcible. Tampering. Can a payment amount be modified in transit? Without request signing or integrity verification, an attacker can intercept a $100 payment request and change it to $1. Gap identified. No request integrity verification on payment flows. Repudiation. Can a customer deny placing an order? Without comprehensive audit logging, yes. Gap identified. Admin panel queries bypass the centralized audit trail entirely. Information disclosure. Does the API leak other users' orders? Without proper authorization checks on list endpoints, an authenticated user can view every order in the system. Gap identified. Missing row-level security on database queries. Denial of service. Can an attacker exhaust the Redis cache or flood the API? Without rate limiting, absolutely. Gap identified. No API rate limiting or cache eviction policies. Elevation of privilege. Can a regular customer access administrative endpoints? Without role-based access control enforced at the gateway, yes. Gap identified. Admin endpoints are not segregated or protected by additional checks. 6 stride categories. 6 critical gaps. This is exactly why threat modeling works. It systematically finds what your penetration test might miss. Let's now correlate our assets, threat actors, and existing controls. Our critical assets are 1. Customer personally identifiable information in the database. 2. Payment card data in transit. 3. JWT authentication tokens. And 4. Complete order history. Our threat actors are external hackers attacking from the public internet, malicious insiders with legitimate admin access, and compromised third-party payment processors. Our current controls include TLS 1.3 for data in transit, JWT for authentication, role-based access control for the admin panel, and a web application firewall for the frontend. Now let's map. Customer PI is protected by TLS and RBAC, but threatened by both external hackers and malicious insiders. The gap? No database encryption at rest. Payment data is protected by TLS, but threatened by external hackers via man-in-the-middle or supply chain attacks. The gap? No payment tokenization, raw card data transits through our system. JWT tokens are protected by digital signing, but threatened by external hackers. The gap? Weak signing algorithm and no token rotation policy. Order history is protected by RBAC, but threatened by insiders. The gap? Missing comprehensive audit logging. This three-way correlation matrix exposes precisely where your controls fail against your actual threat actors. This is the core deliverable of threat modeling, not a list of threats, but a prioritized list of control gaps. Threat modeling is not optional. It is the foundation of secure software development. Start every project with a data flow diagram. Apply Stride to find technical threats systematically. Apply LINDDUN when personal data or privacy compliance is involved. Correlate your assets against your threat actors and your existing controls. And most importantly, do this before you write the first line of code. If you found this valuable, subscribe to Evoluguard Academy for more cybersecurity deep dives. Let me know in the comments what system you would like me to threat model next. Stay secure.